In the electric potentials and fields lab, you will measure electric potentials or voltages and then calculate electric fields. So there you have a water tray and two brass cylinders that you will use as point charges. It's a very crude approximation, but it works a little bit. So you have to place those in the water tray, and there is a grid underneath that. There's some markings here, so I just place it on the markings. I'm not very careful right now. Then you will have to put some charge on there. So to do that, we use a little transformer that will plug into the wall. So looking at the specs of the transformer, so that's what it looks like. The input is 115 volts AC, so whatever comes out of the wall. The output is 14 volts AC. So I'm going to plug this in a little bit, but I want to check this value so that I would know what settings to use for my voltmeter, for my DMM. So here's my voltmeter, and since I'm to measure alternating current, I'm going to have to use this scale, and the maximum voltage according to the specs of the transformer is 14 volts, so I'm going to have to turn this a little bit higher than the 14 volts, so that would be 40 volts, the 40 volt scale. Then I will have to plug cables in, and I'm going to use a ground, plug this into the volts jack. This measures voltage, so here it is. And the cables that I'm using have this end to them. I'll show you how to use them in a little bit. But so now I have my voltmeter all set up. Before I plug in the transformer, I'll show you what the other two ends, the other end looks like. So we change this a little bit, and some of you will have just two alligator clips at the end. Some of you will have two connected to the same wire, and the reason that we did that is so that it's easier for us to clip like this to the edge of the water tray, and then we can plug in the ground to the voltmeter here so that we don't have to hold it with our hand. And then this will be connected to here. This other clip will be connected across the other charge. And now, and only now, will I plug this into the wall. All right, so I'm ready to take measurements. So I will show you the voltmeter display. So right now, the voltmeter is showing 0.27 volts for no reason, 0.3 volts for no reason, because the other end of the voltmeter is actually still in my hand. I'm not touching it to anything. But if I touch it here, you'll notice that the voltage goes down to 0, which is what we would expect, because I'm essentially shorting out the voltmeter, because both the black cable and the red cable are connected to the same terminal of the transformer. Okay, so again, I'm plugging this here, and I'm getting 0. Now, if I'm touching the other terminal, my voltmeter is actually going up to more than the 14 volts that the transformer promised, so I have 17.6 volts. Okay, so the maximum voltage is going to be 17.6. The next thing I'm going to do is I have to take data. So I have to measure the voltage along the x-axis, and I'll do that by inserting this perpendicular into the water tray, and then I'll record the voltage that I get there versus the location where this was. So I have to take the coordinates of the point where I'm touching this, then I'm going to move it to a different location and then measure the voltage. I'm going to move it to a different location and measure the voltage. So everywhere along the x-axis, wait for it to stabilize a little bit and then record that value, and also the x and y coordinates. Of course, on the x-axis, the y coordinate is 0. So measure this everywhere along the x-axis. Then measure it all along the y-axis as well. So let's put it here somewhere, and I'm getting about 10 volts. Then I'll move it over there, and I'm getting about 10 volts. So write these values down, move it up a little bit. I'm at about 10 volts. Then I will want to measure equipotential surfaces around one of these charges, as it were. And since it's symmetrical, I can just use one quadrant, so I can use the first quadrant. And let's say that I'm going to put my probe in the water at this location and read 6.32 volts. Then I will find 6.32 volts somewhere else in the tray. That's too much. How about here? That's better. So I will record this value and again the coordinates of this point. Then I'll move somewhere here. That's too much. How about there? No. It's going up. There we go. So find several different points, find a few points along each equipotential surface so that you can draw the equipotential lines. Then choose a different value for the voltage. And now I have 9.04. I will find 9.04 somewhere else. So just probe in the water until you get that value. Okay, so you will do this with several different points. Now, once you are done with plotting the equipotential surfaces for this dipole, you will want to use the second configuration. To change the second configuration, you first have to unplug the transformer from the wall and then disconnect the charges, the two cylinders really, and then set up a parallel plate capacitor. You need to follow the instructions in the lab manual so that you know what the separation between the capacitor plates should be. All right, so here we have the parallel plate capacitor. Now I'm going to plug the transformer back into the wall, and I will measure equipotential surfaces again. So 7 point, it's going down. 7.5 max, I guess. Okay, so equipotential surfaces will be parallel to the capacitor plates for this. So find a few of those. Again, only work in one quadrant. Also measure the voltage along the x and y axes. And once you've done that, the third configuration has this cylinder inside. So you have to do the same types of measurements with the cylinder in there. You will also have to measure the voltage inside the cylinder at different locations. Okay, and you'll notice that it's going to stay pretty much constant. All right, so once you have all the data, you can draw the equipotential surfaces and then draw the electric field lines perpendicular to those equipotential surfaces. All right, that is EPF.